Welcome to the third video on notes of intervals of increasing and decreasing. And in the previous video, we learned the ways in which a function could increase and the ways in which a function could decrease. Okay, so let's actually talk about a couple vocabulary terms before we do some specific examples. The first thing you want to understand is if you see this type of shape, looks like an upward parabola, this is called concave up. Okay, and functions that are concave up, such as this point here, you could think of this as a turning point, among other things. Now, what makes this a turning point? Well, think about what it means to turn around, right? So if somebody's, walking along, right? This is a horrible picture, right? Going this way and just taking a stroll, okay? If they want to turn around, what they're going to do is they're going to actually change direction. They're going to go, instead of going to the right, they're going to pivot, turn around, change direction, and they're going to go left. Okay, so to turn around means to change direction. So in a function, right, the way that I like to think about this particular function is as I am traveling along the x-axis, I am decreasing, right? My y values are decreasing here, but then I hit this turning point and all of a sudden my y values start to increase. So I call it a turning point because the y values change from decreasing to increasing, right? They essentially turn around. So that's a turning point. Now, similarly, I could have a function that is concave down. It kind of looks like an upside down bowl, if you will. So this is called concave down. And, a function that is concave down can also have a turning point, and similar logic applies, right? So this point up here, this is called a turning point. Why? Well, because the y values actually turn around as we go from left to right. Remember, we're always reading left to right. So here I'm walking along and the y values are increasing, going up. And all of a sudden, when I hit this turning point, the y values start to decrease. So they turn around at the turning point. Okay, now let's not confuse a turning point with an inflection point, okay? With a turning point, as we just saw, the function changes direction from increasing to decreasing or decreasing to increasing. However, if we have something like an inflection point, and you may remember one of the famous examples of an inflection point, the parent function y equals x cubed, kind of looks like this, okay? An inflection point is a point at which the function changes concavity. So this is called an inflection point. All right, so what do I mean by that? So let's look at the left-hand side of the function. Do you see that from here to here, right? The function looks as though it is concave down. It's sort of like this upside down bowl. So here the function is concave down. If I had to describe it as I travel along the function from left to right, I would say that I am increasing at a decreasing rate, right? And then all of a sudden at this particular inflection point, it looks like I'm concave up because I'm sort of upward facing, right? So I change concavity. And here I am increasing at an increasing rate. So an inflection point is not a turning point. They are not the same. An inflection point simply means I change concavity. What's interesting about y equals x cubed, however, is that the function is actually increasing the entire time, right? As I travel from left to right along the x-axis, I'm always increasing. The y values are always going up. Now, how they're going up is changing slightly, but the y values are always going up. So an inflection point is a change in concavity. In the next video, I will do some specific examples using the interval notation that we've learned in the past to identify intervals of increasing and decreasing.